So we'll follow the great presentation by Christine. Now me, I'm a bedrock geologist, so we'll focus on some aspects dealing with the bedrock geology on this specific area. As Christine said, the first part, or the first year of the project was try to understand the source of the significant sulfate content of groundwater in this area. And what is very particular is the fact that the groundwater has a very wide range of sulfur isotopic ratio. So what we want to do is all the sulfate in the salina group, can that explain the widespread distribution of sulfate isotopes in dissolved sulfate in groundwater? So I will address this issue and where we are going into our research right now. So this is a very schematic map of the geology, bedrock geology of southern Ontario. The geology is divided in two major tectonic domains. First, to the west, we have the Michigan Intracratonic Basin, and to the east, we have the Appalachian Fallen Basin. These two basins of very similar age are separated by a tectonic eye, which is the Algonquin Arch and the Findlay Arch, separated by the Chatham Sag. So these two areas evolve in distinct tectonic environments starting in the middle of the ocean, but they share fairly similar stratigraphic succession. As seen on the slide, the study area outlined by the ellipse is located in the Appalachian Fallen Basin. And you see also the Bruce area on the slide, which is in the Michigan Intracratonic Basin. This is a very important area because there's been a lot of work on the Paleozoic units there, and I will refer to that area in a few slides in the presentation. To the right, you have the stratigraphic column of the area. So our work interest today will focus on the Guelph and Salina units in the stratigraphy, both Silurian in age. Last year, most of the work was focusing on characterizing the evaporites in the salina group. In the salina, you have gypsum and anhydrite. The work was try to see if there is any differences in the isotopic composition between the gypsum and the anhydrite that could explain the widespread range of values of sulfur isotopes in the sulfate in groundwater. The graph in between the visual characterization of these sulfate shows the isotopic values for sulfur and oxygen for both anhydrite and gypsum. As you can see, both units have very similar sulfur isotope values between plus 25 and plus 30, which are typical of marine sulfate. The difference resides in the signature, the oxygen isotope signature, with the gypsum being isotopically very light, which is the consequence of the hydration of anhydrite in the presence of light meteoric water. So the problem we have now is that these isotope values cannot explain the widespread of the anomalous values that we find in the groundwater, the dissolved sulfate in groundwater. As you can see on this slide, the rectangle represents what Christine christened the stew corridor, which is the area, a very specific area where we do have very anomalous, very light sulfur isotopic values in dissolved sulfate. This area, we also have the normal marine sulfate derived from the salina, but this specific area has there's an extra source of sulfate that needs to be explained. So to summarize this, what I just said is that in yellow, you have the range of sulfur isotope from the sulfate into salina group, which is between plus 25 and 30, normal marine. And in the groundwater, you also have a terrestrial component between -2 to +15, which is not present in the salina evaporites. One potential candidate for supplying this type of isotopic values in groundwater is the Queenston Formation at greater depth, in which you do have gypsum from terrestrial origin. Okay, so how can you then envisage the migration of these sulfates from great depth into the aquifer? This is a long-term objective. What we are going to do today is just try to start to work on that aspect, looking at, is there any evidence of fluid flow migration from greater depth towards the surface? One critical element that we will use in the remaining part of the presentation is the hydrothermal dolomitization model, where fluid migrate along faults rooted in the Precambrian basement, moving upward into the succession. This is a model that has been developed in the Bruce Peninsula in the Michigan basin. So fluids migrate from great depth. Okay, so what are the evidence of maybe fluid or fault control fluid migration in the area of interest? The Niagara Peninsula is a very interesting area because in this area you have the connection, you have the junction of many Grenvillian domains that are juxtaposed in this area. This results in the presence of a large number of faults and compressive structures that are present in the Precambrian basin. On the slide to the left, you see in rectangle, with the orange rectangle, the location of the anomalous domain with respect to these lineaments that have been mapped over the years. We're lucky enough in 2009, there was a high-resolution aeromagnetic survey that was shot over the Niagara Peninsula. This is what is shown on the right. So this is the second vertical derivative of the magnetic signal, which outlines lineaments. So magnetic lineaments in the Precambrian basement. We're not seeing the platform because the platform is too thin and there is no magnetic minerals in those successions. So what we see is the expression of magnetic lineament in the Precambrian basin. If we put the geological map over this geophysical survey, we have two major first-order lineaments that have been recognized, not only in this study, but previously. This is the HLEL, which is the Hamilton-Lake-Erie lineament to the left, and the NPLZ, which is the Nipigon-Pickering lineament zone. These two are two major first-order magnetic lineaments, in between which we do have the anomalous domain and a large number of second-order lineament at angle with the main lineament domain, and in which we do see some displacement of lineament. A lineament, a magnetic lineament, is only the expression of a magnetic mineral alignment. It's not necessarily a fault. It could be, but it has to be proven seriously. When you see displacement of lineament, this is an evidence of faulting. But we have better evidence in this area because in the early 2000s, there was a lithoprobe seismic program that was shot in the southern part of the Niagara Peninsula. You see the small black line that has just added onto the slide to the left. This is part of a seismic profile that I will show in my next slide. So this is a seismic profile that was shot for the lithoprobe, which was designed to image the Precambrian basement, the deep subsurface in this area. But the quality of the acquisition was so good that we were able to image the shallow platform rocks overlying the Precambrian basement. So what we see on this seismic profile are a number of faults, a large number of significant faults, most of which are rooted in the Precambrian basement, so below unit number 1 that we see on the slide. So, and these faults cut through the platform rocks all the way to the surface. So we have a large number of faults that are present in the study area as seen on this seismic lines. One critical aspect for the hydrothermal dolomitization model, as I mentioned previously, is these elements. These are called seismic sags. These are the seismic expression of faulting, fracturing, and migration of high temperature fluid that will dissolve the carbonates and precipitate dolomite. So we have here evidence in the Ordovician, that's the Ordovician succession, so the Trenton Black River interval, of hydrothermal, dolomitization, porosity generation, permeability, but also in the Silurian succession, higher up in the stratigraphic package. This is the Guelph formation. So we see the Guelph also affected by faulting, leading to brecciation and dissolution. So we have the first step of formation of an aquifer. We generate porosity in the dolostone of the Guelph. Let's go back now to the area of interest and how can we document the migration of high temperature fluids in this area? Because these are old events, they're Silurian in age. Do we have any evidence in the rock record that these high temperature fluids were likely present in that time? So we will use two thermal data sets to evaluate this possibility. The selection of these, all the stars that we see on these slides and the dots on the one to the right are cores that were collected by Abigail project in this area. And we selected some cores to cover the area of the anomaly, so the rectangular area, but outside also this area. So first part of the project will look at the organic matter maturation. So in the Salina group, there's some black shells. And in these black shells, you have organic matter. If the organic matter experience the anomalous high temperature, it will react and generate higher thermal conditions, record higher thermal conditions. So we will evaluate that by doing some hot pyrolysis. So we cook the organic matter and we'll release hydrocarbons at a certain various steps that indicate what kind of temperature this organic matter has experienced. And we also add organic matter petrology where we can characterize the reflectance of the organic matter, which is a direct indication of high temperature, various temperature events. To the right, we show what we're going to do with the dolomite of the Guelph Formation. We will be studying mineralogy in the Guelph, various specific minerals that might be indicator of high temperature conditions. Let's have a look at the preliminary results. First, the organic matter study. Both type of studies, so the pyrolysis, the hot pyrolysis, you burn the organic matter, and also the petrographic observation, both type of data indicates that there is anomalous higher temperature event recorded by this organic matter. They are in the oil window from both techniques, and this is an anomaly because when you look at the source rock, the organic matter rich Ordovician succession well below the Silurian units, they are marginally in the oil window. So it's the presence of higher thermal conditions in the Salina matrix indicate that some of the sample, not all of them, but some of the sample experience higher temperature conditions, higher than normal burial temperature. Now for the Guelph, we have completed our conventional petrography of the dolostones, and we have recognized multiple mineral and various events in the succession. The main mineral phases have 3 types of dolomite, 2 types of calcite, and 1 type of celestite, all separated by various fracturing, dissolution, and compaction events. So we have a paragenesis succession from early to the top left of the slides, all the way to late and deeper in the right, bottom part of the slides to the right. The important elements that we will focus after that are the presence of what we call saddle dolomite, celestite, and late blocky calcite. You'll see the importance of these minerals later on. Just a few quick images of the petrography. So we have done conventional petrography under the conventional microscope, but also cathodoluminescence petrography, which is very critical to identify subset of mineralogy within a specific mineral. So you see the various type of dolomite and celestite, saddle dolomite, a lot of shearing, fracturing is visible in thin sections, and also the last one to the right is very important, celestite and late blocky calcite for the rest of my story. Now we do have these minerals. What we now are trying to do is to characterize these elements in function to understand what they are recording as, as fluid that led to their precipitation. We'll do oxygen and carbon stable isotopes in dolomite and calcite. This slide here shows you the values of the same cement, exactly the same cement that we see in Bruce Peninsula, in the Silurian, the Guelph Formation and Bruce Peninsula. Those are the field of data that is currently available in the literature, but we're still waiting our own data, so we should get them by March. Then after that, we are currently looking at fluid inclusions microthermometry in the same minerals. The importance of fluid inclusion is that these tiny fluid inclusions that are entrapped in minerals record the conditions at the time of the mineral precipitated. They record the temperature of precipitation of this mineral and also the salinity of the fluids at the time of precipitation of the cement. So also on this slide, you see the field for the saddle dolomite and the blocky calcite and celestite from the Bruce Peninsula area. In red is the limit of the maximum burial temperature. So anything to the right of that red box indicates very high and normal hydrothermal fluid affecting the Guelph at that locality. Again, we should expect our own results shortly, I hope. I was hoping to have them here, but not yet. So this is work in progress. Now, if we plot early information that we have on the map with the anomaly, when we look at the organic matter, so the map to the left, we do see anomalous thermal conditions recorded by the organic matter, either from the pyrolysis or from the organic matter petrography in the anomalous domain, and slightly one sample out of it. The other sample do not record any anomalous eating. The same can be said for the dolomite. We do have, if we take for granted that the late saddle dolomite and calcite and celestite are, as in the Bruce Peninsula, indicator of high temperature conditions, we also have a lot of sample in the anomalous domain that are recording these high temperatures. Now this is my last slide. So how can we, what are we going to do with these data, with these information? One aspect interesting, in one of the many aspects of interest, is the presence of these faults in the area and the presence of some earthquakes associated with the trace of these faults in the subsurface. The slide to the right is an old slide in which all report of earthquakes have been compiled, historical, oral, and written reports with very few instrumentation documentation of the earthquakes. To the left, this is a slide from the GSC, or the Natural Resources Canada Earthquake Database, plotting only the events higher than 2 in magnitude from 1980 to today. What we see, there is some significant event at many in this area, and all these events are associated with these faults that we see in the hydromagnetic domain. One final aspect of interest is the locality just north or northeast of Toronto, along the Red River, where we do have some quaternary sediments of the Scarborough Formation that are cut and displaced by faults. And these faults also cut the black shale, the Ordovician black shale in this area. So is this only an event that is related to relaxation after the melting of the glacier, or is there a tectonic component associated with that? We do have also evidence in the Lake Ontario that there is a tectonic component clearly associated with the formation of these faults. So earthquakes are really active in this area. So what are the significance for that? We'll see. So this is a summary or the preliminary conclusions. What is important is that we do have now good evidence of high temperature fluid migration along faults in the Silurian time. We also have regional evidence of such fluid migration in the Ordovician and in the Devonian. There is also recent study, uranium-lead dating of calcite in some faults associated with the same area, which indicate that there was an event of reactivation in migration of high temperature fluid leading to calcite precipitation in Cretaceous roughly 100 million years ago. And we have some decent evidence of reactivation of these faults in the Quaternary or the very recent age. So as a conclusion, the significance of these faults for modern fluid migration has to be better investigated. And this is what we're currently doing. Thanks a lot.